Welcome, everybody. All right. Okay, how's it going? Looks like Fam, or not Fam. Looks like Sanders has been doing a lot of stuff. So there are definitely things I can talk about. If you guys have any questions about the homework, I can certainly address them. Or we can move on to one of the many other things that he has been talking about. I'm going to say no to 7 because we did a problem just like 7 last class. So if you want to go back and look at the end of the class from last time, you should definitely look at 7. We can look at 8 though. So we can look at 8 because 8 is similar to 7. They both require the same sort of process. We can definitely talk about 9 and 10 for sure because those look kind of weird. Okay. Ooh, all right. And then you guys should think about if you have questions about the things he's been saying in class. Because I know in the last couple of classes, he has talked about a lot of things. He's talked about implicit differentiation, related rates, exponential growth and decay, and the inverse derivative theorem. So if there are any of those things you want me to talk about, let me know. But let's go ahead and let me see. Love the orange pens because they don't erase as well, but they're the ones I have the most of. So yeah, let's see. We'll try and use the other ones, and then if they run out, they run out. So let's look at a problem similar to number 8. So let's say that we have a function. I feel like my board's kind of far back. Let me switch it up a little bit here. A little bit better here. Let's say we have a function g of x equal to f of x over h of x. And this is going to get old real fast. And let's try these blackboards. And here's what we know. We know that f of 7 is equal to 1. F prime of 7 is equal to 8. H of 7 is equal to -3. And h prime of 7 is equal to 4. And using all of that information, we're going to figure out what g prime of 7 is. So we're being asked, what is g prime of 7? Really, this is just a question that asks, do you know how to use the quotient rule? Just like the previous question, problem 7, is really just asking, do you know how to use the product rule? So I feel like I'm going to turn off this lamp back here. I think it's not providing illumination the way I wanted to. Well, let me open these windows a little bit. I think that's better. Okay, so I know that if g of x is f of x over h of x, then g prime of x, using the quotient rule, it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Yeah, these black pens are just about dead. Okay. So the idea is now we're just going to say, well, okay, if g prime of x is this, g prime of 7, we're just going to plug in a 7 wherever we see an x. So that's going to be h of 7. Yeah. I'll close this one up. Get that in there. Times f prime of 7 minus f of 7 times h prime of 7 all over h of 7 squared. And then we know what f of 7, f prime of 7, h of 7, h prime of 7 are. So we're just going to plug those in. So this is going to equal, so h of 7 is negative 3, f prime of 7 is 8, and then f of 7 is 1, and h prime of 7 is 4, all over h of 7, which is negative 3 squared. And we just do the arithmetic. We get negative 24 minus 4 all over 9, which is negative 28 over 9. So that's how you do a problem very similar to problem 8 and 7. You just use the product or the quotient rule to write out what the derivative is. So like for problem 7, the derivative of h of x would be f prime of x times g of x plus f of x times g prime of x. And then you would plug in 3 and use all the known values to figure out what the derivative is. Let's see here. There's the attendance again. Let me not use these black pens anymore. Should I throw them in the trash? I don't think I'll throw them in the trash just yet, but they're pretty much trash. Okay. So, people also have questions about 9 and 10. Let's look at 9. And, oh, that's a boring question. I'm going to change it up a little bit. Let's make it interesting. Let's say my function f of x is equal to cosine of x cubed plus 2x 12 minus 12. And I want to find the equation of the line tangent to this function at the point x equal to, I think x equal to 2. So I want to find the equation of the line tangent to f of x at x equal to 2. This pen's probably also trash. Sorry, I'm trying to get through all my trash pens so they don't use it anymore. So hopefully you can kind of see what that says. This says equation of the line tangent to f of x at x equal to 2. So whenever you're asked to find the equation of a tangent line, you need 2 things. You need a point and you need a slope. We have half of the point, right? We have the point 2 comma something. Well, the y value is just f of 2. So we can plug 2 into that function to figure out what f of 2 is. So this one's going to be, I'm going to change up just a tiny bit if you don't mind. Let's make it plus 7x squared. I know the slope's going to be something not interesting if I don't change it, so make it a little different. So our function is this, and I want to find first the point. So I'm going to plug in 2, and I'm going to get, let's see, so f of 2 is cosine of 2 cubed, which is 8, plus 2 times 2, which is 4, minus 12, plus 7 times 2 squared. I simplify this, I get cosine of 0 plus 7 times 4. And what's cosine of 0? Yeah, exactly. Thank you, Elsa. So we know that our point is just 2 comma 29. And then we need the slope. And the way you find the slope, when you're talking about calculus, is you find the derivative and then you plug in your point. So to find the derivative here, we're going to have to use the chain rule. So again, I'll remind you, the chain rule says if you're taking the derivative of a function of some stuff, the chain rule is you take the derivative of the outside part, you leave the inside alone, and you multiply that by the derivative of the inside. So here's how I'm going to think about this. I have any red pens? Yeah. So I'm thinking about this function, so this part, whatever. I'm thinking of that as some stuff. So I'm taking the derivative of cosine of x. I know the derivative of cosine of x is negative sine of x. In a similar way, the derivative of cosine of some stuff is equal to negative sine of that stuff times the derivative of the stuff. So the derivative of cosine of the stuff is negative sine of that same stuff. We're going to have to multiply by the derivative of this stuff, which is 3x squared plus 2 minus 0. So I really think of this as sine of some stuff times the derivative of that stuff. Sorry, I just should have said negative sine of some stuff times the derivative of stuff. So you always leave the insides alone when you're doing the derivative of the outside part, and then you multiply that by the derivative of the inside part. And then we've also got this, the derivative of 7x squared is 14x. Oh, that's fine, yeah. So plugging in 2, f prime of 2 is going to be negative sine, let's see, 8 plus 4 minus 12 is 0, times 3 times 4 is 12, plus 2 is 14, plus 14 times 2. And sine of 0 is what? Well, if you know cosine of 0 is 1, sine of 0 has got to be 0. So you get 0 plus 28, which is 28. So here's what we've got. We've got, I've got not enough room. Let's go to the other side. So I've got my point of 229 and my slope of m equals 28. Sorry, that's not what I said. So the point is this pen is dead. This one can go in the trash, I think. Yeah, lots of pens. So the point we have is 2 comma 29, and the slope is m equal to 28. So here's kind of the idea, right? You've got some function. All my pens dying. It's all right. Bound to happen. So here's what's going on. We've got the graph of this thing, and it just looks kind of like whatever. Maybe this is I'm pretending like this is the point 2 comma 29, and we've got some tangent line with a slope of 28. So to find the equation of this line, there's a couple ways you can do it. My personal favorite way is to use the point slope form. So the point slope form, if you've got some point x1, people call it like x1, y1, or x naught, y naught. If you've got some point and some slope, then you say y minus y naught equals your slope times x minus x naught. I would recommend memorizing this. Where this is coming from, actually, if you really want to know, is we're really just saying, well, I'm trying to write the equation of this line. So let x comma y be any point on the line. Then we know how to find the equation of the slope. The slope is y minus y naught equal over x minus x naught, right? The difference in the y's over the difference in the x's has to equal the slope. And then we just multiply both sides by the denominator. So this is what I usually remember as how to find the equation of a line once I know the point and the slope. The slope is 28, and the point is x is 2, and y is 29. So my equation is y minus 29 equals 28 times x minus 2. And I think you're fine leaving it like this, but some people are not. So then you'd want to solve for y and say y equals, so distribute here, 28x, and 28 times negative 2 is minus 56. And then we add the 29. So we end up with y equal to 28x. Negative 56 plus 29 is minus 27. So once you have a point and a slope, that's how you find the equation of the line. There are other ways to do it. If you prefer, you can do it this other way, where you just say, well, I know it's going to be y equals mx plus b. And then you can say, well, the slope is 28. And then you can plug in y equal to 29 and x equal to 2, and then solve for b. And you get the same thing. You're going to get 29 minus 56, which is negative 27. And then you plug that back in here. So that's another way to do it. This pen also dead. It's a day to kill some pens. Okay, So whenever you find the equation of a line, this is how, of a tangent line, this is how you do it. You find the slope, you find the point, and you throw them into this equation. Okay. So let's look at one similar to 10. 10 is an interesting question. Let's see if I can make something up that's good here. I'm sure I can. Let's see if this green pen is any good. I'm going to set a little pen tray over here. Kind of. You guys don't care. Doesn't matter. Let's see. So we've got this. So let's say that g of x is equal to f of x to the third. Yeah, that'll work. And here's what we know. We know that tricky, Sanders, real tricky. Okay, sure, that's fine. Huh. Let me think for 1 second. All right. So we're going to need to know that. I could be lame about it. No, even that's not going to work. He wants you to do that. Second derivative. Okay, fine. So my problem is going to be slightly different. That's right. So let's say we know this. We know that f prime of, sure, 3 is equal to, I don't really care. And the f double prime of, so his is interesting in that he gives you that and that. Sure, that's tricky. Okay. All right, well, let's see. I'm dumb, sorry. Sorry, I tried to help with this. It's hard to make this problem actually work out the right thing. So let's do this and then we'll kind of see. So here's what he's asking you to do, right? He's asking you to find g double prime at some value, which we'll fill in a minute to kind of make it make sense. Not that this thing's so here's how we're going to find g double prime. So we're going to find g prime. Well, I'm taking the derivative of f of some stuff. So just as an example, right? Let's pretend like g of x was actually a given function. Let's say it was, I don't know, let's say it was sine of x cubed just for a minute. Then if I was going to use the chain rule, g prime of x would be, well, the derivative sine of some stuff is cosine of the stuff. And then what should I be multiplying by? This is where I wish we were in a classroom, because I would say, and everyone should say we're multiplying by exactly, but more generally, I would say the derivative of the stuff. So whenever I'm asking you a question like this with the chain rule and I say, what should we be multiplying by? The answer I'm usually looking for is the derivative of the stuff, which is exactly 3x squared. So in this case, I don't actually know that my function f is sine, but I know that whatever the function is here, the derivative of that outside function shows up there. So the derivative here, more generally, is f prime of x cubed times 3x squared. Same kind of deal, except instead of using cosine, or sorry, sine and its derivative of cosine, we're using f and its derivative f prime. Okay, and then we're going to do the same thing again. We're going to find the second derivative. Now, second derivative is going to be a little bit more interesting because we have to use the product rule additionally. So I've got this piece times this piece. In fact, before we do it here, let's do it over here. And this red pen is also starting to go. Okay, so to find the second derivative, we're going to do this piece times this piece. So the derivative of cosine of x cubed, well, we're going to take the derivative of cosine. The derivative of cosine of some stuff is negative sine of that stuff. And then I need to multiply that by the derivative of this stuff, which is 3x squared. And then I also need to multiply by the other piece over here. Right, so let me point out that this part right here, that's the derivative of cosine of x cubed. And then this part here is just that part. So it's the derivative of this times that, plus, then we do it the other way around. You get the derivative of this, which is 6x times, you leave this alone, cosine of x cubed. So hopefully that seems somewhat clear what's happening. So to find the derivative here, so the derivative of f prime of some stuff, well, the derivative of the derivative is the second derivative. So the derivative of f prime of whatever is f double prime of that stuff. Then we have to multiply by the derivative of that stuff. So right here, there's the derivative of this. But then we have to multiply by 3x squared. Plus, then we do the other part of the product rule. We leave this piece alone, f prime of x cubed, times the derivative of this, which is 6x. Okay, so now here's the question I could actually ask. So I had to work it out before I could figure it out. So here's the question I want to know. If I'm given that g of x equals f of x cubed, I want to find, and I also know, let's see, what do I need to know? I need to know that f prime of 8 is whatever number I want to make it. Let's make it 3. And f double prime of 8 is, I don't know, 4. Then I want to find g double prime of 2, right? Not g double prime of 8. I want to find g double prime of 2. Because when I plug in 2 for x, I'm going to get 2 cubed here in the f double prime and in the f prime. So I'll have to use f prime of 8 and f double prime of 8. So let's take a look. G double prime of 2 is going to be f double prime of 8 times 3 times 4 times 3 times 4 plus f prime of 8, right? Again, I'm putting in 2 for x times 6 times 2. So I end up with some I probably could have made better choices for my answer. Let's see, f double prime is 4, so I get 4 times 3 times 4 is 12. 3 times 4 is 12. And then f prime of 8 is 3 times 6 times 2 is 12. Let's see, I've got 12 times 12 is 144 times 4 plus 36, some number. This is what? I don't know. 288 times 2 is 576 plus 36, so you get 612. Doesn't really matter what the number is here. The point is that you can take the second derivative of g of x equal to f of something by doing, so g prime of x is f prime of the something times the derivative of something. And then the next derivative of that, so the derivative of this is f double prime of the stuff times the derivative of the stuff times the other thing that was over here, and then this thing times the derivative of that thing. And then you just plug in x equal to whatever number specifically g is being evaluated at. So you're going to also do g double prime at 2. Since you have x squared here, that will give you f prime of 4 and f double prime of 4. So hopefully you guys can attack problem 10 now. It's definitely a kind of a wonky problem, but I think it's pretty doable. Yeah, it should look very similar to what we have here, where you have f double prime of something times the derivative times the other thing here that should probably look the same as that, and then you'll have f prime of something times just the derivative of that. Okay. Sure, we can definitely do one like number 4. Again, number 4 is kind of similar to this problem, in that we're again finding the equation of a tangent line. The difference with number 4 is that we're also having to use the quotient rule. Also, I want to mention, just generally, I saw that I think today in class, Sanders is supposed to talk about the derivatives of the trig functions. Or maybe he did that last class. Anyway, I did post a video showing all the derivatives of the other 4 trig functions, as well as sine and cosine. So if you need help understanding how to find the derivatives of the trig functions, they're on a video already. I would recommend to all of you to memorize the derivatives of the trig functions. They will come up over and over and over again in 17A through C. So you might as well just memorize them as soon as you can. Okay. So a question similar to 4. All right, so let's say we have this function, f of x equals, his function is not my favorite, so let's do something more fun. Something like, I don't know, x cubed plus cosine of x over, yeah, x to the fourth plus 1. We'll see how this turns out. And we want to find, again, the equation of the line tangent at x equal to 0. It started out as a parenthesis, but tried to turn it to an x. It didn't work out so well. Okay. So just like the other problem where we found the equation of the tangent line, we need a point and we need a slope. We have half a point. So let's find the other half of the point. So the point is going to be 0, comma f of 0. Right? We know the x value is 0. We want to find the y value. The y value is going to be, let's see. If I plug in 0 here, f of 0 is 0 cubed is 0, cosine of 0 is 1, 0 to the fourth is 0, cosine plus 1. So our slope is 1. Or sorry, our point is 1. Our y value, our y coordinate of the point is 1. So there's our point, 0, comma 1. No, I'll just leave it at that for now. So then we have to find the slope. So to find the slope, we're going to use the derivative. And I would just find the derivative generally. And then after I find the derivative, plug in x equal to 0. So finding the derivative, I get the bottom times the derivative of the top, which is 3x squared plus, that's going to be lame, plus negative sine of x minus sine of x minus the top, x cubed plus cosine of x times the derivative of the bottom. Oh well. Sorry, there's something that's not fine. It's fine. Over the bottom squared. And then we plug in 0 to see what the slope is. Now I will tell you the slope is going to be less exciting than I want it to be. I'm going to modify this problem in a minute to just kind of show you something slightly different. Here's what we get. We get f prime of 0 is, let's see, 0 plus 1 times 0 minus 0, right? Because sine of 0 is 0, minus 0 plus 1 times 4 times 0 cubed is 0, all over 0 plus 1 squared, which is 0 over 1, which is 0. Slope of 0 is never exciting, but it is still a line. So here's my equation. I'm going to do the same thing I did before. I'm going to do y minus y naught equals the slope times x minus x naught. In this case, that's going to be y minus 1 equals m, which is 0, times, I really don't write anything here, but I'm going to anyway, x minus 0, right, because the x coordinate is 0. Now, 0 times whatever is 0, so I really get y minus 1 equal to 0, which is y equal to 1. When you have a tangent line that has a slope of 0, that means you have a horizontal line. It means you should always get y equal to just a constant. Let's see what happens if I change this just slightly so that it's a little bit more interesting. Let's say the denominator happened to have a plus 2x as well. So it was really x to the fourth plus 2x plus 1. The point actually doesn't change because if you plug in 0 for x, you still get 0 plus 1 on the top, and you still get 0 plus 0 plus 1 on the bottom. So you still get 1 over 1. But then my derivative is going to be a little bit different. It's going to be, so it's going to be the bottom, which is x to the fourth plus 2x plus 1 times the derivative of the top, minus the top, which is x cubed plus cosine x times the derivative of the bottom, which is now 4x cubed plus 2, right? Because the derivative of x to the fourth is 4x cubed, the derivative of 2x is 2, divided by the new denominator squared. Okay, if we look at that instead, just for a different flavor, we plug in, if we find f prime of 0, let's see, I get 0 plus 1 times 0 minus 0, okay, minus 0 plus 1, right, because cosine of 0 is 1. Sorry, 0 plus 1 is 1. Times 0 plus 2, which is 2. all over 0 plus 0 plus 1 squared. So I end up with -2 over 1, which is -2. That's a little more interesting. So now the equation of this, the tangent line for this function, x equal to 0, would be y minus, well, so I should, I know, I still going to do it the way I want to do it. I'm going to do y minus 1 equals m, where m is -2, times x minus 0. Which then I can write as y minus 1 equals -2x, or y equals -2x plus 1. In this particular case, you probably didn't need to do all that work at the end there because you already know the y-intercept is 0, 1. So you're just going to be like, oh, if my slope is -2, then my intercept is 0, 1, then the equation is y equals -2x plus 1. And you can kind of jump to that if you happen to know the point is the y-intercept. Okay. So I'm thinking we should talk about implicit differentiation. So I feel like this class is moving kind of fast. Like I feel like all of a sudden we just got to like all the derivative rules all at once and all the applications pretty quickly. So if there are things you would like me to make videos of, like I'm thinking I might do a couple of video examples of implicit differentiation, maybe some related breaks, because I know we talked about that on Friday or maybe Wednesday. I don't know, we talked about it a while ago. So there are things you want to see, either write a discussion in Canvas or send me an email, and I will try to make that happen. So there's a few things I want to remind you of before we start talking about implicit differentiation. And that is really that we have the chain rule. So the chain rule, super important to get a grasp of. And it just says what we've been saying. Right? If you have a function of a function, in fact, let me write it out. So here's the chain rule. Right? You're taking the derivative of f of g of x. Right? A function of a function. The way it always works is you differentiate the outside, you leave the insides alone, and then you multiply by the derivative of the inside. Whereas you will hear me say it over and over and over again. You take the derivative of the outside, you leave the inside stuff alone, and then you multiply by the derivative of the inside stuff. It's always how this is working. And so it works for kind of any function we know how to differentiate. So here are the derivatives we kind of know already. And we know the derivative of x to a power is n times x to that power to the n minus 1. The chain rule version of this is, well, instead of x, we're going to say we have some stuff. So if I've got the derivative of some function to the nth power, it's going to be n times my function to the n minus 1 power times the derivative of that function. An example of this, we've actually done a couple, but here's another example, right? The derivative of, I don't know, let's say sine of x plus x to the 8th to the 10th power. So here's what I'm seeing. I've got the derivative of some stuff to the 10th power. I know the derivative of x to the 10th is 10 times x to the 9th. I know the derivative of some stuff to the 10th is 10 times my stuff to the 9th times the derivative of that stuff. Where my stuff is sine of x plus x to the 8th. And then the derivative of that stuff is cosine of x plus 8x to the 7th. Now, if I actually left my answer like this, I feel like it'd be a little bit wrong. And here's why. It looks like I'm multiplying all of this by just cosine, and then after that, I'm adding on 8x to the 7th. So if you've got more than one piece for the derivative of your stuff, we have to have parentheses around that. There's just no other way around it. Some other functions we know how to differentiate. We know that the derivative of sine of x is equal to cosine of x. So we know a chain rule version for this. We know the derivative of sine of some stuff. So like sine of f of x is cosine of the stuff times the derivative of the stuff. So for example, the derivative of sine of x to the 7th plus 4x squared plus 1 is equal to, well, the derivative of sine of some stuff is cosine of the stuff, x to the 7th plus 4x squared plus 1, times the derivative of the inside stuff, which is 7x to the 6th plus 8x plus 0, which I'm not going to write. So whenever you're using the chain rule, the thing that's the inside function should kind of show up again, right? Sine doesn't show up again because it's taking the derivative sine of some stuff, but the derivative sine of whatever has to be cosine of the same thing, and then multiply by the derivative of the insides. In the same way, we have a rule for cosine. Okay. So, right, if I'm taking the derivative of cosine of x, it's equal to negative sine of x. And then if I'm taking the derivative of cosine of some function or some stuff, it's negative sine of that function or of that stuff times the derivative of that stuff. So here's what I would like you guys to do. I'm going to give you like a minute. Find the derivative of cosine of x to the 5th plus 3 sine of x. Go ahead and try that. I'll give you a minute. I'm going to charge my Fitbit. I'll give you approximately a minute since my second timer is not available to me. I don't know if it's really been a minute. I'm going to tell my guys. So the derivative of cosine of this stuff is negative sine of that stuff. So negative sine of x to the 5th plus 3 sine of x times the derivative of all this, which is 5x to the 4th plus the derivative of 3 times sine of x is 3 times cosine of x. There we go. I think there's one other function we kind of know how to take the derivative of, and that's an exponential function. So we know the derivative of e to the x equals e to the x. So the derivative of e to the stuff is e to the stuff times the derivative of that stuff. So for example, the derivative of e to the x squared plus cosine of x is equal to e to the x squared plus cosine of x times the derivative of x squared plus cosine of x, which is 2x minus sine of x. And I think that pretty much covers the functions we've talked about differentiating so far. There's still a few left, like the other 4 trig functions and the logarithmic functions. But now knowing this, you can take the derivative of any kind of composition of functions where you have any one of these things, like you have e to the stuff, or cosine some stuff, or sine some stuff, or some stuff to a power. Oh, I've got a good handout. I might need to send you guys. See if I can find it. So, I keep looking at my wrist. Yeah, okay. Yeah, I said implicit differentiation. We won't get there. This was like, just do one more. Let's say I want to do the derivative of, and this one's going to look kind of gross. Yeah, let's do it that way. e to the x squared times sine of x to the fourth plus 1. So this is kind of a gross derivative because not only is there a product rule, there's also the chain rule for each of these pieces. That's okay, we can handle it. So whenever we do a product rule, it's the derivative of the first part times this part. So I'm going to do the derivative of that. Okay, the derivative of e to the x squared is e to the x squared times the derivative of x squared, which is 2x. Times, leave this alone. Right, you're always differentiating one piece and not differentiating the other piece. Plus, then we leave this piece alone. And we take the derivative of this piece. Which I'm using d dx to represent that. So the derivative of sine of some stuff is cosine of that stuff times the derivative of the stuff, which is 4x cubed. I will point out, I didn't put the 2x in parentheses or the 4x cubed in parentheses since they were only one term. It wasn't necessary. So that would be our derivative. All right, let's talk about implicit differentiation. So the whole idea with implicit, there was one other thing, sorry. I wanted to send you guys, just one sec. I wanted to remind you guys about the online drop-in tutoring that is available. If you ever want to make an appointment, you can go to that website and utilize the online drop-in tutoring. There's lots of availability. So if you're looking for help, because I'm not always available, that is a place you can get some help as well. And there is the attendance form once again. So, implicit, which I feel like I start on a new page, but whatever. So implicit differentiation. So the whole idea behind implicit differentiation is we are assuming that y is a function of x, even though we might not actually be able to explicitly show it. Kind of a classic example, and I think you did one like this in class, is something like x squared plus y squared equal to 9, or something like that. Because we know that that equation doesn't represent a function. Right? X squared plus y squared plus 9 is a circle of radius 3, center to the origin. And it's not a function, right? It doesn't pass the vertical line test. Right? Not a function. But things that aren't functions still have derivatives, right? You can still think about the slope of the tangent line of this function. And one way to do it, which is the lame way to do it, which we're not going to do, is you can solve for y and say, like, the top half of the circle is y equal to the positive square root of 9 minus x squared. And then the bottom half is y equal to the negative square root of 9 minus x squared. That's totally fine. You can totally do that for this example and take the derivatives that way if you really, really want to. But one, it's worse because it's just not as nice. But more importantly, two, you can't always do that for the things we're going to see in the near future. So we're going to do this other thing. We say, well, I'm going to pretend like y is a function of x, even though it's not. But it's close enough, right? Y mostly depends on x, so it's okay. And then if you want, actually, let's do it this way. So I'm going to write this as x squared plus f of x squared equal to 9. And then we're just going to differentiate as is. We're not going to try and solve for y or f of x. We're just going to differentiate. So what's the derivative of x squared? 2x. What's the derivative of some stuff squared? Oh, we're going to use the chain rule. It's 2 times my stuff to the first power times the derivative of that stuff, which is f prime of x, equal to the derivative of 9 is 0. So then we can solve for f prime of x, which is right here. So let's see. So I've got 2 times f of x to the first power, so let's write 2 times f of x, times f prime of x equals, subtract 2x from both sides, negative 2x. And then solving for f prime of x equals negative 2x divided by 2 times f of x. Canceling the 2, so you get f prime of x equals negative x over f of x. Or if you use y's instead of f's, you can say y prime equals negative x over y. And then you can Say, well, I want to find, say, I don't know, the derivative at the point. Sorry, I erased my circle. But like you got a point here, like, I don't know, 1 comma the square root of 8. I want to find the derivative there. I just plug in x equal to 1 and y equal to the square root of 8. And you get y prime of 1 equal to negative 1 over the square root of 8. And it should be negative because the slope of the tangent line there is definitely the negative tangent line, or negative slope tangent line. So that's very quickly in a nutshell what we can do with implicit differentiation. We can use it to find the derivatives of equations that aren't really functions of x, but are close enough. So let's do another example, an example where you actually really have to use implicit. So let's say we had something like, I don't know, x cubed y squared plus xy equal to 15x plus x to the 4th. Okay. And I want to find y prime. So I'm going to pretend like y is a function of x, and I'm going to differentiate using the chain rule. So the derivative of x cubed times y squared. So the derivative of x, so I'm going to use the product rule. So it's going to be the derivative of x cubed, which is 3x squared, times leave y squared alone, plus x cubed times, now here's the thing. The derivative of y squared isn't just 2y, because y I'm pretending like is some stuff, right? I'm really thinking of this as, this is some stuff squared, where y is the stuff. And the derivative of some stuff squared is 2 times my stuff times the derivative of my stuff. My stuff is just y. So it's 2 times y to the 1st times y prime. Plus, okay, same deal here. I have to use the product rule. Derivative of x is 1 times leave y alone plus x times, what's the derivative of y? It's going to sound like a dumb question in a second because the derivative of y is just the derivative of y. You can also say it's 1 and then multiplied by y prime, but as I say, well, I'm taking the derivative of y, it's just the derivative of y, which is y prime. Equal to, okay, you got 15 plus 4x cubed. After this first step, the rest is all algebra. We're going to group all the y prime things together. There's the thing that has a y prime, right? That's the y to the first. And there's the thing that has y prime. And everything else we're going to put on the other side. So since these are already on this side, let's just keep them here. So I'm going to simplify this as 2x cubed times y prime plus x times y prime equal to, I'm going to subtract these things over to the other side. 15 plus 4x cubed minus y minus 3x squared y squared. And then I'm going to do 2 more things to solve for y prime. I'm going to factor out a y prime. That's why I brought all the y prime terms to one side and all the other terms to the other, so I can factor out a y prime term, y prime. So y prime times 2x cubed y plus x equal to the same stuff. And then finally, divide both sides by this, so that y prime equals all of that divided by this. So 15 plus 4x cubed minus y minus 3x squared y squared divided by 2x cubed y plus x. That is the derivative of this equation at any point xy. Let's do, we're out of time. I was going to do another example, but I think we're out of time. So Wednesday, we'll talk more about implicit differentiation. If you guys have questions, don't hesitate to ask them. Here's the attendance form one more time, just to make sure you all got it. And yeah, I will see you on Wednesday. You guys are doing all right. Oh, for those of you in FAM's class, if you have questions, don't hesitate to send me a message too. And you guys have a midterm coming up. So yeah, I know his class meets like right now, so you might not be here. But if you are here, feel free to send me a message and let me know. All right, I'm going to end it.